Welcome to the webinar, Redefining Decarbonization Beyond Energy Optimization, sponsored by CIM Magazine and Saskatchewan Research Council. I am your organizer, Michelle Beacom, Managing Editor of CIM Magazine, and my co-organizer is Ryan Bergen, Editor-in-Chief of CIM Magazine. Just a little housekeeping before we get started. I don't think you can see my slides, can you?
No.
Sorry, they were shared. There we go. Sorry about that. If you joined by computer audio, please make sure you've selected the computer audio button on your GoToWebinar control panel. If you joined by phone, please make sure you've selected the phone button. If you have questions during the webinar, please make sure you select the question mark on your GoToWebinar control panel and type your question into the question box. And now I will turn the webinar over to Ryan to introduce today's presenter.
All right, well, thank you very much, Michelle, and thank you to everyone for joining us today. Today's presenter is Dr. Erin Powell, who is a Director of Strategic Initiatives and Business Development at the Saskatchewan Research Council. During her 15-year tenure at SRC, Erin has served in a variety of roles, including most recently as manager of SRC's process development team. And then also later, Erin will be joined for the question period by Lucinda Wood, SRC's business development mining lead. Now, over to you, Erin.
All right, I will just share my presentation. Everybody can see that, hopefully. All right, welcome everybody. As Ryan mentioned, thank you for that lovely introduction. My name is Erin Powell, and we'll be talking about redefining decarbonization beyond energy optimization this morning. So I'd like to begin with SRC's land acknowledgement. Greetings and acknowledgement, or as we are on Treaty 6 territory in the homeland of the Métis. We pay our respects to the First Nations and Métis ancestors of this land and reaffirm our relationship with one another. We understand the importance of acknowledging the past and embracing a future where Indigenous peoples and their traditions are valued and supported. Together, we strive for a more inclusive and equitable business environment that benefits all. So this morning, I'm going to talk very briefly about the Saskatchewan Research Council. I'm going to define some key concepts. Some of this might be information you've already heard, but I want to make sure we're all on the same page with the terms and the concepts before we launch into the additional content. We'll talk about Canadian and mining emissions context, and then we'll get into the decarbonization beyond. So what do we do now, and can we do more in this area? I'll discuss the challenges to implementing emissions reduction solutions, how we can best determine a solution for a client's emissions reductions, some of the lessons that SRC has learned in working from other industries than mining, and how we can support industry in determining the best solutions. And then we'll conclude with some next steps for the mining industry. So briefly, the Saskatchewan Research Council, with who many of you may be familiar with, is Canada's second largest research and technology organization. And we support industry, government, and communities to develop and demonstrate technology around the world. And we've been doing so for over 75 years. So we work with academia, technology developers, industry, government, and we have clients both in Saskatchewan, we have clients nationally and globally that we support. So defining the key concepts. So what are greenhouse gases? These are often referred to as GHGs for short, and these are gases that absorb infrared radiation, so net heat energy that's emitted from the atmosphere, and these gases re-radiate it back to the Earth's surface. So the reason they're called greenhouse gases is you can think of this as being similar to what happens with the greenhouse. It lets in the heat energy and then it is captured and trapped in the greenhouse, increasing the temperature. So there are natural greenhouse gases in the atmosphere: water vapor, carbon dioxide, methane, and ozone. And these are all naturally occurring, but some of them are also increased by human activity. And there are also human-generated greenhouse gas compounds, such as hydrofluorocarbons and perfluorocarbons. So the Canadian National Inventory tracks 7 greenhouse gases that are released by human activity. And the 2 primary ones on this list are carbon dioxide and methane that you probably will have heard about. but they do track nitrous oxide, sulfur hexafluoride, and as I mentioned, these fluorocarbons and nitrogen trifluoride. And I do want to make one other point before I move on. This is what we're referring to when we talk about greenhouse gas emissions. So this is different from pollutants in waste airstream emissions, which can also be harmful for different reasons. So you may have pollutants and you may have greenhouse gas emissions in a waste stream, and they are two different things that need to be dealt with differently. So a couple of other terms I'd like to explain: climate mitigation. So this involves avoiding and or reducing emissions released into the atmosphere. So reducing those emissions can involve changing to processes or energy sources that emit less greenhouse gases, or capturing emitted GHGs to prevent their release. So this can be done on an individual site basis, a project basis, a company basis, a jurisdictional basis, or an industry-wide basis. It is reducing what is in our control. Climate adaptation, however, is the process of adjusting to actual or expected climate changes and their effects that are out of our control. So in order to minimize the negative impacts and potentially take advantage of any opportunities that may actually arise from the scenario. So climate adaptation is focused on impacts of climate dynamics and adapting to them. So that can be related to water security. It can be related to site or industry preparedness for extreme weather like floods or fire, developing alternative vegetation plans that are adapted to new climate situations. So one other term I'd like to define is carbon dioxide equivalent. So you might see this written as CO2e or sometimes as CO2eq. And what this is really a basis that allows us to compare different greenhouse gases on the same basis. So the formula for this is really you take your amount of gas and you're multiplying it by your global warming potential. So different greenhouse gases have different global warming potentials. Often this potential is a number that's calculated over 100 years. You might see numbers over 20 years. But the point here is that these different greenhouse gases have these different GWP. This table here on the right, you'll see that methane's GWP is 28 times that of carbon dioxide. So what that means is if you have the same mass of methane as carbon dioxide, the global warming potential, the impact of that methane will be 28 times greater, apologies. And this just allows us to compare different greenhouse gases on a standard basis when we're looking at our emissions. So a couple of carbon reporting concepts for everybody. Carbon reporting refers to the reporting of greenhouse gas emissions using CO2 equivalent. Many jurisdictions do require reporting on greenhouse gas emissions in order to measure and claim impact of any reduction measures. Another term you may have heard but not be familiar with is life cycle assessment, or LCA. And this method of measuring environmental impacts across a product's life cycle. So what we call cradle to grave analysis of a product. And these impacts do include greenhouse gas emissions. So they're part of the LCA is your carbon footprint, but it also includes energy consumption, water usage, and waste generation. One other carbon reporting concept that I'd like to explain is scope 1, 2, and 3 emissions. So these are categories used to describe an organization's footprint. They're greenhouse gas emissions based on their point of origin. So scope 1 emissions are probably what people are most familiar with. These are direct emissions that are owned or controlled by a company. So these can be managed as desired. Scope 2 emissions are actually indirect emissions. So these are from purchased energy sources. So this would be electricity you're needing to purchase, energy for heat, cooling, or steam for company operations. And these are typically managed by using lower carbon intensity and renewable energy sources. So that would be one of the routes there to reducing those types of emissions. However, there are also scope 3 emissions. Now, these are another source of indirect emissions from sources that are not owned or controlled by the company that's looking at their carbon reporting, such as supply chains and stakeholder relationships. So the concept of scope 3 emissions can be a little bit confusing to define. So I'm going to give you an example here. This would just be an example of what would be included in scope 1, 2, and 3 emissions, just an example mining operation, for example. So scope 1 emissions are direct emissions. These are the emissions coming from our company facilities that are operating, from our company vehicles that we're using. Scope 2, the indirect emissions. This is our purchased energy, electricity, energy for steam heating and cooling for the company to use. And then we get into these Scope 3 emissions, and these can be including upstream activities. You can almost think of it as activities from suppliers coming into your facility, and downstream activities. So think of that as maybe customers and distributors of whatever you are producing. So these Scope 3 emissions can include transportation and distribution, purchase goods and services, and fuel-related services, waste management, business travel, and employee commuting would be part of that Scope 3 upstream. Downstream, again, transportation distribution is always a big one when it comes to emissions. Processing of sold products, use of sold products, the end-of-life treatment and disposal of our sold products, and in both cases, leased assets would also be part of Scope 3. And so that can get a little bit complex when you're looking to define your overall emissions, because those Scope 3 emissions are often shared, well, they are shared with other companies. So we've defined some terms, but what is net zero then? So net zero, I'm sure that you've all heard more talk of achieving net zero in recent years. So net zero is the state of total greenhouse gas emissions being zero. And that can be done on a site basis, a company basis, an industry basis. And how can we achieve net zero? So we can either be removing our produced GHG emissions, or we can be removing atmospheric carbon to balance our produced GHG emissions. So there's two routes there to achieving net zero. And this can be achieved in multiple ways, such as energy utilization reduction, and direct methods like CCUS, which stands for carbon capture, utilization, and storage. And before I move on to defining CCUS, I do want to make one other point here for mining, is that mining is actually key to the net zero transition for other industries. And that's because of its role in extracting and processing critical metals. And those are necessary for electrification and for green technologies like batteries and renewable energies. So that's critical to helping other industries achieve net zero, not just mining itself. So what do I mean by CCUS? Okay, so as I said, that stands for carbon capture, utilization, and storage. Now I have here and or storage because although it is all one term, we are not always doing all of these steps. So what do we mean by capture? Remove carbon dioxide either from our industrial greenhouse gas emission sources. So one example would be flue gas from combustion, or from the atmosphere. Utilization, so that is taking the CO2 that we have captured and using it in other processes that need CO2, or converting it to other useful products. And I'm going to talk about some examples of both of those in a minute. And then storage, that's where we're safe and permanently storing that CO2 over a very, very, very long term, what we would look at making permanent. So what about the term sequestration? So I'm not really going to use sequestration in this presentation because it can get a little bit confusing. Sequestration is often used when we're talking about capturing CO2 from the atmosphere for a wide range of applications. It's frequently used when we're talking about biological technologies and solutions. So I'm not going to use it here in the presentation. Just for clarity, we're going to keep what you capture, utilization, and storage so that we're clear what type of processes we're talking about. So Canadian and mining emissions context. So how large are Canada's greenhouse gas emissions? So in 2022, which is the most recent year we have numbers from the Government of Canada for, 708 megatons of carbon dioxide equivalent was emitted, and that's an increase of just over 1% from the year before in 2021. The total greenhouse gas emissions from heavy industry were 89 megatons of carbon dioxide equivalent, and mining is part of heavy industry. So that isn't mining alone, that's all of heavy industry, that number. Between 1990 and 2022, our greenhouse gas emissions increased by over 16%. But this is where timescale comes in, because if we look at the change from 2005 versus 1990, we see that the emissions have decreased by over 7%. And 2005 is when we really started looking at greenhouse gas emissions here in Canada. And so the point of this is that we are definitely making progress now that we've taken some action on emissions. So Canada's emission targets, Canadian and global regulations continue to evolve as targets become more aggressive and impact more industries. Canada has a 2030 emissions reduction plan, and the goal there is to achieve a target of 40% reduction below those 2005 levels I mentioned by 2030, and we're looking for net zero emissions by 2050. And there are some new actions for heavy industry, which includes mining, that were mentioned there. Certainly additional emissions reduction efforts to decarbonize large emitters. But the other point here, which is something we're talking about in this particular webinar, is the Government of Canada is looking for a comprehensive CCUS strategy. So they want to look at development and deployment of CCUS technologies to mitigate greenhouse gas emissions from a range of industrial sectors, which does include mining. And mining emissions are under scrutiny. So public perception, stockholders, government are taking a look at increasing numbers of industries regarding their emissions. And another point is just many markets are asking for different greenhouse gas emissions data and targets. So for example, if you want to sell your product to certain markets in Europe, you need to be reporting scope 1, 2, and 3 emissions as part of that product. So there are a lot of considerations even outside of existing regulations when it comes to greenhouse gas emissions targets for an individual company or industry. So what greenhouse gases are produced by mining? Well, many of you are probably aware that the primary GHG from mining is carbon dioxide. And it comes from fossil fuel usage, electricity transmission, and when we're looking at the wider scope of emissions, goods and services, and product use. Methane is primarily emitted by coal mining, both active and abandoned mines. So a lot of our focus today is going to be around CO2, as that's the primary concern for mining. There are many types of emission sources. So these include stationary combustion sources, mobile transportation sources, processing and manufacturing sources, and fugitive emission sources. So those are the emission sources, those little sneaky ones here and there that individually are often small, but can add up to significant emissions when you put them all together. So recent estimates are that mining makes up less than 10% of global emissions. So I have a table here, and this table is actually limited to the facility greenhouse gas reporting program. So we're talking about large emitters in this particular table. But I just wanted to include the breakdown for this subsector of mining, quarrying, and oil and gas extraction of where the emissions are coming from for the large emitters that are reporting. So the largest proportion is oil sands extraction, followed by oil and gas extraction, accepting those oil sands. And then as you can see here, metals mining, non-metallic mineral mining, and quarrying and coal mining are that less than 10%, which is the same situation we're seeing globally as we're seeing in Canada. So one interesting thing to note, though, is that emissions from mining have risen actually since 2005, while other types of emissions have been falling in Canada. So overall, they rose 36% between 2005 and 2022. So now the question is, why have emissions from mining increased if industry has been investing in decarbonization and improving efficiency? And in fact, emissions intensity has been reduced per unit of energy. So that's the good news. But the reason we still have more emissions presently from mining is two reasons. Increased economic activity. So the mining industry has absolutely grown significantly in the last 20 years. So we are doing more mining, even if our emissions intensity is lower. And increased energy intensity per unit has also increased in many cases. We've got fewer accessible high quality ores. We have more mining operations that are extending deeper underground and occurring in more remote areas. And then of course, obviously there's some challenges with both of those that require additional energy usage. So now moving on to decarbonization and beyond. So what are we doing now in mining, and can we do more? So the mining industry has definitely made progress, as I mentioned, in recent years towards decarbonization. We talked about energy intensity and emissions intensity on that last slide. Mining operations have reduced their emissions, and there's two major focuses that they've been using so far. So looking at optimizing operations and equipment selection to minimize energy consumption, and switching to lower carbon intensity sources. So electrification and employing low carbon or net zero intensity energy sources, and finding efficiencies is an ongoing process though. And it is especially challenging, as I've said, at remote mines. So can we do more? Well, with regulations and public perception changing, we now need to look towards an integrated solution to GHG emissions reduction via more direct mitigation routes. And so that's where we bring in this capture, conversion, utilization, and storage. So other industries have implemented these direct mitigation routes to meet regulations and targets. One example is oil and gas here in Canada with more recent methane regulations. So they've been doing that through capture, utilization, and storage. And here I'm referring to CCUS because we talked about how CO2 is the primary emission for mining, but obviously you can do capture, utilization as well for methane. Another approach, integrating industries or facilities to offset net emissions. So that's where you integrate different types of industries or facilities together. Maybe one facility's waste product is another facility's feedstock, and that can be a route to reducing emissions. And then very key, what we're finding is integration of multiple strategies to optimize the resulting emissions reduction and economics. And I don't want to forget about economics. I'm going to bring those up again later because we always need to consider what is going to be cost effective and practical when we're employing these types of technologies and solutions. So what we can do then going forward is combine efficiency and low carbon energy sources with CCUS technologies to provide an integrated solution for reaching net zero. So some examples of CCUS, capture of CO2. So this is where we're looking at capturing our industrial waste streams before they're released to the atmosphere. So an example is carbon from fossil fuel combustion of flue gas. And these applications are simplest if you have a large point source versus if you have a lot of small sources. So these are some of the considerations. The other option for CO2 capture is extraction of CO2 from the atmosphere to offset produced emissions. So direct air capture. And then there are also quite a few land-based and ocean-based methods. I won't get into those here, but certainly accelerated weathering, afforestation, looking at direct ocean removal, microalgal cultivation. There are quite a few options for extraction of CO2 from the atmosphere as well. So I have a schematic here to just sort of sum up at a high level the approaches we can take in CCUS. So we start from our carbon capture, whether we're collecting our own GHG emissions or whether we're removing CO2 from the air to balance our emissions. We can take the route directly to storage, which would be geological storage long term. The other option is utilization. That's the U in our CCUS. So there is utilization for things like foods and beverages and enhanced oil recovery. Now, the differences between storage, utilization, and conversion are sometimes not well defined. And the example is enhanced oil recovery. This would be utilization of CO2 to improve production from an oil and gas reservoir, but much of the CO2 actually remains in the reservoir, so it can also count as storage. And then if we're not doing direct utilization, that is where we are converting when we use the CO2 into a useful product that may have value or may further offset our emissions. So as a feedstock for fuels, chemicals, and agricultural applications, to make cement for backfill, as well as some biological approaches such as using microbes or microalgae to produce valuable products. So on the topic of the carbon utilization, I just have another graph here just showing some more examples of direct use versus indirect use. So direct use is utilization. Indirect use, that's where we use this term conversion often because we need to undertake some type of chemical process to convert our CO2 into something else that we want to use. So fuels, chemical intermediaries, plastics, building materials, cement and concrete. And then if we're using it directly, there are actually more applications than you might think. Solvents for decaffeination and dry cleaning as a heat transfer fluid, welding and medical uses, as well as, of course, yield boosting for things like greenhouses, fertilizer, and algae. So we've talked about very conventional carbon storage examples, EOR plus storage, geological storage, but I did want to mention a couple of non-conventional carbon storage examples. The first one is bioenergy plus carbon capture and storage. So this involves specifically using biomass as an energy source and combining that with, which is really part of the capture, and combining that with permanent storage of CO2 produced during the conversion of biomass to energy. And this has multiple outputs, primarily power generation. And SRC actually recently engaged in a project similar to this for a client where we were looking at where would you do the storage, where would you obtain your CO2 from this biological source, and looking at mineralites, drilling, transportation, a lot of practical applications to implementing something like this, depending on where your site is. The last non-conventional carbon storage I wanted to mention is carbon mineralization. And I have a couple of slides on this because we've had a lot of interest in carbon mineralization from the mining industry recently. So this is a natural process in which minerals take carbon dioxide from the air and create carbonate rock. So this is actually a naturally occurring process, but it occurs over very long time periods. And so right now, researchers are developing a way to accelerate that process in industry, especially for mining. And so the output there would be carbonate rock, but that would be a type of CO2 storage where CO2 is captured from the air and is stored long-term in this carbonate rock output. So carbon mineralization. As I mentioned, it's an innovative new carbon capture and storage technology that is being researched. You may have heard it referred to as mineral carbonation, mineral sequestration, or enhanced rock weathering. Because as I said, there's a lot of interest in this right now, so I wanted to make sure we were familiar with all the terms. So this is where we have fresh surfaces of rock or minerals, and they convert carbon dioxide either from the atmosphere or from a carbon gas stream. So we could use captured emissions from a site for this to mineral form. It's mineralized on the rock material, and that is potentially of all sizes, so from powder to rock outcroppings. And if carbon mineralized material is mixed with soil or at grade, it can be used by plants, bacteria. So there's a lot of research happening in this area because there's a lot of applications for this. So some examples of some of the technologies that are presently being worked on by various parties is applying rock dust from mine tailings or aggregate operations to agricultural or residential soil, spreading rock dust along coasts for weathering with waves, tides, land farming mine tailings, tilling dry tailings material to expose it to the atmosphere, and chemical and physical processing of mine tailings with combustion exhaust to store carbon. So what are some of the challenges to emissions reduction solutions? So regarding GHG emissions mitigation challenges, one of the primary ones is the temporal nature of operations. So we can often have a very intermittent greenhouse gas emissions flow. We don't always have the same amount of gas from day to day, hour to hour, month to month. We can have low variable quality gas. So depending what you want to use your emissions for, the composition does matter. We can have low volumes, we can have low gas pressures. Geographically isolated locations can be a challenge, and lack of access to infrastructure for implementing mitigation solutions. So before we get into how we're going to mitigate these, we need to talk about measuring and identifying our sources. And there are a lot of challenges with this. All sources may not be easily identifiable or quantifiable. Data availability may be limited and the quality of the data may be poor. There's a lot of variability in emissions, and measuring and monitoring can be actually quite challenging. There are practical issues. Standards and methodologies are not available for all types of emissions. There are a wide range of standards and methodologies, and so we may need to develop and validate new ones depending on the scenario. And then how accurate does our measurement need to be? It depends on what we're trying to accomplish, and how accurate it needs to be impacts how we need to measure those emissions on a site. Also, incorporating shared emissions can be complicated. For example, those scope 3 emissions I talked about, where we're talking about upstream and downstream activities, they can be particularly challenging because of the complexity of tracking emissions across the entire value chain and the various stakeholders involved. So I want to give an example. This is actually an example from oil and gas. They've done a lot of work in recent years around their emissions. And so I just have a very simple schematic here of a very generic well site. We have our wellhead, we have an emulsion tank, we have a truck that would be collecting emulsions and taking them to a treatment facility. And as you can see, it's not so simple to determine what are our greenhouse gas emissions. You've got casing gas from the wellhead. That gas can be vented directly to the atmosphere if that's allowed. It may be going to a flare or a combustor. It might be getting gathered to go to a pipeline, depending on where you're located. You might be using it for fuel on site. It can also be used in pneumatic equipment, but then that pneumatic equipment also is venting some emissions to atmosphere. And then we also have to consider fugitive emissions. So those are small emissions occurring in small locations throughout the site that are very hard to track and you may not even know are there. We've got gas from the tank vent. And then in addition to sort of this obvious schematic, we need to consider things like gas migration, uncombusted associated gas from heaters and drives and flares and combustors on the site. Associated gas can be lost from seals and packing, starting and stopping compressors and drives. So all that equipment operating on the site, there can be little small emissions losses that we may need to consider. Gas can be vented from oil and water transport trucks. And then specifically to oil and gas, of course, some of the richer components in the oil can flash and be vented from these emulsion tanks, but very intermittently and in different volumes. So this is an oil and gas example, but it really demonstrates how complicated it can be to measure all of your on-site emissions. And this is primarily on-site emissions. This is not even getting into your entire value chain, although of course with the inclusion of the emulsion trucking, that does include emissions that are leaving your site. So when I talked about how complex measurement can be, I wanted to share this table with you. So if you look at Canada's Facility Greenhouse Gas Emissions Reporting Program, so these are large emitters that need to report to the Canadian government, you can see that there are 5 primary methods that various industries and reporting companies are using for measurement. There's a large range. Different methods are accepted, different methods are appropriate, and there isn't necessarily one standard that is acceptable at this time, depending on the industry that you're working with. So a lot of work still needs to go into effective measurement. So what can we do about measuring emissions under these conditions? Well, we can improve data collection processes. We can refine emission factor selection if you are using emission factors, and many industries do need to with unknown emissions. We can enhance measurement and monitoring techniques. We can develop and validate new measurement protocols. We can employ advanced monitoring systems that can be left in place and monitor remotely so that we can collect data over a long period of time to make the best emissions reductions decisions. We can look at more cost-effective techniques. And then, of course, what is very important as well that we found is impartial third-party verification can be very important when you're reporting emissions, depending on who the audience is for that information. So let's talk about, okay, so now we've figured out what our emissions are, we've measured them, we've determined what we need to reduce at a particular site for a particular company, but how are we going to determine what the best emissions reduction solution is? So obviously we have to identify the emission sources we want to consider. So which emissions are within scope? Are we starting with the site? Are we dealing with our entire company? Are we dealing with the entire industry? We need to measure those emissions where possible. As I said, sometimes it's very challenging and we have to make some assumptions or use some different methodologies to get that information. We need to identify our emissions target for reduction. So are we aiming for the 40% reduction by 2030? Are we trying to get to net zero? And then the next step, once we know what our goals are and what we have for emission sources, is to identify strategies and technologies that are suitable for reducing those emissions for the scenario. And that's where it can be important to involve an impartial third party, as there's a very large landscape of technologies and methodologies out there, and it can be difficult to know where to start. And the idea of integrating multiple strategies and technologies, so not one size fits all. The next step, if necessary, is real-world performance testing, if that's applicable. So sometimes we're looking at a new application for a technology or a methodology, or we're looking at a technology that's not quite commercial, so that's where that can be helpful. And then the final step, of course, is to implement our solution. Some of the critical considerations when we're determining what solution will best meet our needs, of course, as I've mentioned, the emission source type, volumes and flow rates, material composition, variability. But other important considerations are the location of the site we're looking at, any transportation logistics, if we're removing things from the site, for example, emissions products or the CO2 itself, if we need to bring in feedstock for inputs, if we're doing some type of conversion, where's our market end user for any outputs we might have. And then the other key thing is we can never forget economics. So what is the capital cost of the solution? What is the operating cost going to be on an ongoing basis? What will the carbon credits be? So that can offset those costs. So that would count actually as a revenue. And carbon credits are expected to increase over time, making things more economical, and any CCUS revenues. So what I mean by that is if we're making a product we can sell by using our conversion technology, then there could be revenues there as well to offset the cost of implementing the solution. What infrastructure do we have, or what will we need to build? What are the local regulations, and what additional labor will we need? So I have an example here of a net zero emissions integrated solution. So this was a project where we were involved in assessing and technology integration of a zero emissions oil site that was being developed. So this was an existing operational site that was to be modified, employing advanced remote electrical monitoring so we can identify optimum energy options and efficiencies. We implemented a hybrid system, so with renewable electrical power and storage, so a microgrid on site. And effective energy usage and emissions monitoring was key to demonstrating what reductions we need to get to net zero, and then to demonstrate that we've achieved them and determine what technologies to employ. And then those low carbon and efficiency approaches were combined with direct capture of existing greenhouse gas emissions for conversion using appropriate technologies. We had direct capture and usage on site. Also, in this case, methane transportation off site to a central hub. And the integration of all of these approaches is really what is key to success if you're looking to achieve net zero. So it's not just that one solution. So what are some of the lessons we have learned from other industries? And I've already talked a little bit about this because I gave you 2 oil and gas examples. Just SRC has done a lot of work on the oil and gas front in the last few years around greenhouse gas emissions. So what have we learned from that? Well, number one, you cannot mitigate what you cannot measure or don't know about. So we have to be able to measure those greenhouse gas emissions, and we have to know what they are if we're going to demonstrate an improvement when we implicate our best solution. And also, we need to know what those are to determine that best solution. One size does not fit all. So there's not one technological solution that will solve everybody's greenhouse gas emissions reductions. We need to really look at each situation on a case-by-case basis. We've also learned that emissions profiles can be vastly different even between sites with similar operations. So those differences do need to be looked at as we're implementing solutions. The integrated solution of methodologies and technologies can best overcome challenges in meeting emissions targets. So again, I'm back to integration. I know I've said it a bunch of times, but it isn't that one size fits all. We need to look at the optimization. We need to look at technology, equipment selection on site. We need to look at low carbon energy sources, and we need to look at direct capture, utilization, and storage to meet all of our targets. We've also found that impartial third-party assessment is critical to success. There are a lot of approaches, there are a lot of technologies out there, there's a vast landscape, and that impartial third party can be very helpful in determining what is best to help a specific client. And then the other thing we found is very important for industries is to prepare in advance of regulations. So emissions regulations are always changing, they're becoming more strict. We have more and more markets that want to see emissions data, even if it isn't required from a regulatory perspective. And so preparing before those become more strict gives us time to find that best solution versus doing something urgently that may not be optimum. So I'm going to talk a little bit, just briefly here at the end, about how SRC specifically supports industry to determine the best solutions. And I have touched on this here and there in the presentation, but I'd just like to summarize that for you now. So SRC does provide services as what we call a catalyst for your energy transition. So a wide range of industries, we are providing these energy transition services. So emerging energy technologies, integrated energy systems, energy evolution, so how we're using energy has changed. And one aspect of that is SRC's Center for the Demonstration of Emissions Reduction. So that is, we refer to that as CeDER. You will have seen the little the little green logo in the bottom corner of all my slides, and I'll talk a little bit about CeDER in a minute. CCUS, and then climate adaptation planning. And I did mention climate adaptation earlier in the presentation. So what are the approaches that SRC takes in helping industry with various emission reductions? So there are 5 we employ: optimization of processes, technology, and equipment selection to minimize energy consumption, switching to lower carbon energy sources, direct emissions reduction through capture, utilization, and storage, integration of facilities and industries to offset net emissions, and then integration of multiple strategies. So all of the above as appropriate to optimize the resulting emissions reductions and economics. So just a little bit more about these different strategies at SRC. So process optimization and energy efficient technology. Key mining initiatives we've successfully implemented to reduce energy intensity include innovative technological developments, equipment selection and process control, optimization and data-driven approaches to decision making. And there are various groups at the Saskatchewan Research Council to support optimization technology development in this area. So minerals processing, hydrometallurgy, pre-concentration and sensor-based sorting, multi-phase flow and advanced instrumentation development are all contributing to optimization and energy efficiency for mining at the Saskatchewan Research Council. Regarding reduced carbon intensity energy sources, this one is also very key for mining, and I know many of you are already engaged in this. Mining, all across the mining cycle, significant electricity and fossil fuel use by necessity in extraction, transportation, and processing. So some of the lower carbon energy sources we've been working with include wind, solar, biofuels, and converted waste. And these technologies that I've just listed here, we've been successfully integrating those for our clients with other conventional energy sources and battery storage. So taking the low carbon sources, taking conventional energy as a backup storage, and putting that all together as a hybrid solution to meet energy needs with a lower carbon intensity. These alternative energy options are based on the operational scenario, existing infrastructure, and site access. So those economics, the required infrastructure, energy supply, and efficiencies of these energy conversions by industry across the mining cycle continue to require expert support, which SRC can provide. So, as I mentioned, we have increasing concern around emissions reductions from mining and changes to public perception and regulations. We're implementing multiple strategies at SRC to reduce emissions across the mining cycle, and that is that integrated approach to reduce costs, reduce energy usage, and emissions. And CCUS is the next step for mining to move towards a net zero emission. So we can think of CCUS as another tool in the greenhouse gas emissions reductions toolbox that we're adding in. And that brings me to SRC's Center for the Demonstration of Emissions Reduction, so CeDER. So it's a unique program. We're combining our world-class expertise in mining across the mining cycle, process optimization, clean and renewable energy, and emissions reductions. And I do want to mention just one other point briefly before we get close to the end of the presentation around CeDER, is we also have mobile facilities that can come out on site if we're looking for measurement or real world performance testing of either methodologies, measurement, or CCUS technologies. So CeDER was developed to provide real world selection, assessment, testing, and demonstration of these technologies. It's independent third-party validation, and it accelerates industry adoption of practical emissions reduction technologies. So very last part of my presentation here is the next steps for mining. So to basically sum up my presentation, we're determining the best approach after the sources are identified of greenhouse gas emissions can be challenging. So whether that is CCUS, whether it's lower carbon energy, whether it's optimization or energy efficiency, and choosing the optimal solution to meet mining's greenhouse gas mitigation needs is going to be complex. Integration of multiple emissions reduction strategies is key to success. It's one method or one technology does not fit all. And an impartial third party like SRC can be critical to navigating the landscape of competing technologies and approaches. There's a lot of options out there, and it can be tricky to know how best to proceed. So before we move on to questions, I just wanted to mention that the Saskatchewan Research Council will be in person at all of these events in March and April. They are also listed on our website. So if you'd like to join us at any of these, our experts will be present if you have some questions. And then I think we are ready to move on to questions, which will be moderated by CIM. I will just put up the slide here with the contact information for myself and Lucinda Wood, who will be joining me for questions.
There she is. Okay, great. Thank you very much for that presentation. Some great material in there. So just a reminder to all attendees, there is a question box in your GoToWebinar control panel where you can add a question. So I guess so. There's one that has been added to the queue that I was curious about as well, and I'm not sure if this is the crowd that can answer it, but about turning waste rock into carbonate material. Do you know, has the SRC investigated whether that might potentially have that rock be acid generating?
Oh, sorry, there was just a bit of background noise there. Can you repeat the last sentence?
Whether carbon captured in rock, carbonate rock, whether that has been evaluated for being potentially acid generating.
So there's lots of, I think the acid generating component is related to sulfides. And there are certain different minerals that we are learning about, and SRC through different projects is learning about certain minerals that are that capture more carbon through through the carbonation process, which is what Aaron referred to as mineral carbonation. That would be a separate consideration from acid mine drainage rocks or sulfides potentially, and I think it needs to be looked on a case-by-case basis. I don't know if the question that is being asked is if you start to carbonate minerals, if that releases sulfides that are then available for acid mine drainage. But I think that really the point is to look at how the carbonation minerals there can absorb, or not absorb, sequester, react with the CO2 on a case-by-case basis. So, this is important in mining, and I think Aaron mentioned that the characterization of any of the feedstocks for mineral carbonation is important, and whether they are used in agriculture, whether they are tailings, whether they are waste rocks. I think the characterization and the different types of minerals, such as mafic-based minerals, which seem to be very favorable for carbonation, that needs to be looked at on a case-by-case basis. I'm not sure if I answered your question exactly, but they're not necessarily related, but it does point to the issue of looking at it on a case-by-case basis, and there's probably lots of things going on if you're starting to convert oxidized carbonate rocks.
Right. Okay. A question that needs to be explored for anyone.
Yeah. That's correct. That's correct. They're doing a lot of research in the area for that exact reason.
Yeah.
For that exact reason.
Okay, great. So based on your experience in mining, what percentage of CO2 reduction is expected from electrification versus energy optimization versus CCUS? Do you have
do I have a number for what percentage of decrease we can get by adding in CCUS?
Well, I think that depends. I think if you have a remote mine that's using diesel, obviously switching from diesel to something else would give you a dramatic reduction. If you're on the grid for hydro, you're using hydro energy, it all depends on the starting point, right? So I think if your starting point, and mining has been looking at low-hanging fruit. I think certain jurisdictions have different types of energy. Obviously, diesel's the number one, and then you go down, down the list. They've been looking at energy sources, at switching out gas-powered vehicles for electric vehicles or hydrogen vehicles, and so it depends on. And this was Aaron's point. What are the biggest sources of your carbon footprint? That's the first stage, and then you go and you attack the low-hanging fruit. And if you have attacked the low-hanging fruit in terms of energy, then CCUS would be the next stage to get to net zero.
Right, yes. And if you're asking, Ryan, like as the industry as a whole, so I think, are you saying, well, if we're here and we've optimized and that got us to here, and now we've done energy, low carbon sources, we've got us to here, and CCUS has gotten us to here. I don't have a number for how that split would be for the exact reason that Lucinda mentioned, because it's very situation dependent.
Right.
And we don't have, I don't think, that level of mining data. I can take a look and see if we can find it, but I don't think anybody has it. exactly what that decrease could be, because mining is really just starting to consider CCUS as another tool in the toolbox as regulations and, reporting requirements change. But that's a number that might be coming as we get more information on emissions from the mining industry and do more work implementing these technologies.
So I think in one of your final slides, you showed like a mobile unit that could be taken to site that can measure emissions.
Yes.
So have you gone to a mine site and gotten a sense of, in early in your presentation, you had a table of different kinds of GHGs and their relative, not intensity, but ability to capture energy or reflect energy. Mm-hmm. Like what is the profile of a mine? I know they're idiosyncratic, but like between those, what is the major contributor? Is it the burning of diesel and heavy oil?
So right now the CO2, I mean, it does depend on the type of mine. The CO2 production from the use of fossil fuels, and use of fossil fuels on site would be the largest contributor. Also, even with electrification, depending on the source of your, if you're burning coal for electrification versus hydropower versus solar versus wind, obviously those all have different emissions profiles. But of course, a lot of mines are in remote locations, and so the use of fossil fuels is a necessity up to this point, and that's where we're looking at what else we can do. So that CO2 from combustion of fossil fuels would be the main contributor, outside of coal mining, which does also have methane production even after the mine has been abandoned. So that's a bit of a special case on the methane front, but it's definitely the CO2 from combustion. And then of course we're talking about that would be mining, but there's also minerals processing, smelting, all of those other operations that are part of mining also use a lot of energy, and all of that produces carbon dioxide emissions.
Yeah, so pyrometallurgical processes, if you have that on site, or steel making, those are big emitters. Those are actually considered large emitters, even outside of, in Canada right now, pyrometallurgical or steel making operations are a big source of emissions. And I would also say it's not just about the emissions that are produced. There are missed opportunities, because we've discovered that some minerals can absorb carbon dioxide. What is happening is there are carbonation type processes happening in minerals processing or in tailings that we're missing the opportunity to reduce emissions through that. So it's not just the emissions producing, there are opportunities to actually reduce or capture carbon dioxide, or convert carbon dioxide through some of these minerals processings and tailings through these minerals that we're discovering are natural converters of carbon dioxide.
And then I just wanted to mention just about the trailers, because you sort of started from that point, Ryan. So yes, we do have mobile facilities. And so we do a lot of site visits depending on the type of project. And sometimes that's just sending personnel. Sometimes it's sending one of these mobile facilities, and they can be used for measurement. So different types of emissions measurement on site. And then they can also be used for performance testing of technologies. So if you're going to implement a new technology for capturing your emissions, for utilizing your emissions, for converting your emissions, that could be installed on site, tested. We could gather performance data. If you want to have that type of performance testing before implementing something on a larger scale, or even if you're looking at a technology that has never been used in this exact application, that can be very valuable. So yes, we have the ability to go on site, and not just in Saskatchewan. I mean, the trailers are mobile. We can tow them to where we need, assuming that there's a way to get there. So yeah, that is an option for both measurement and implementing technologies and methodologies for direct emissions reductions.
And I think your point about the emissions measurement is important for the mobile trailers, because air is harder than water and solids to measure. And so that's why it's important to do field testing for air measurements. It's not the same as liquids or multi-phase flows that involve solids. And so that's why we have that ability. It's needed for air monitoring or measuring.
Yeah.
And I think when we have sort of a overlap of mining and carbon capture, there's one of the methods that's been explored is the underground carbon storage. and I believe using excavated voids, often potentially mines. Has the SRC done a lot of much work on looking at the long-term ramifications of underground carbon storage, like seismic implications, groundwater quality, soil quality, or is that a little out of scope?
So we have certainly done as far as the pre-feasibility for these types of underground storage projects. So some of that would be in scope as a consideration, but we haven't gone down the route of like that long-term research regarding carbon storage. So in general, this is not always the case. We do sometimes do our own research, but often what we are looking at is either implementing existing technologies for clients. So for example, a mining company would come and say, hey, here's my situation. What's my profile? What is my solution? Or helping technology developers advance their technology. So we aren't often developing our own technology, which is actually very valuable to our clients because we aren't marketing our own solution, right? We're looking at impartially, we're looking at what the options are. So I would say that would be out of scope, looking at long-term geological effects of carbon storage, but certainly all of that is considered when we're doing that pre-feasibility assessment of where you're going to do that storage and what's going to be involved, and mining rights and drilling and all of those things. Did you want to add something, Lucinda?
Yeah, so if you go, I would recommend everyone to go to the carbon capture conference that's held in Alberta. Oil and gas companies have been doing lots and lots of monitoring, and we would be involved in the monitoring. So we wouldn't be scoped to necessarily look at those effects, but we would be utilized to measure them. And so there's a lot of projects in Alberta done by oil and gas companies to look at the long-term effects of storage, including seismic, including how the CO2, if it comes out of solution, or so there are lots and lots of projects, and I know there are large pilot projects in Alberta that have been looking at this issue for 20 years. I think because storage has not been long-term, we monitor and measure it as much as we can. And oil and gas companies have been doing that for decades. But in terms of 100-year storage, we can only try and do 1 in 100 events at this stage. So that is, I would say, not an open question, but just because storage is relatively new, it's a question we're going to have to answer. And that's why it's really, really important to monitor and measure everything that you're doing.
And we do work frequently with partners. Like if we, as you say, this is an out of scope, like in some cases, maybe what they want to know is that slightly out of scope specialty. We work with partners all the time on projects that involve, quite a sweeping scope, so that we can do different portions of it, arrive at that optimum solution as well. So certainly, if we need to work with a geological partner.
Or PTRC, who've been doing a lot of underground storage.
Yeah, so we do that as needed for projects, and we're open to working with anyone and having multiple partners on a project as needed, so that we get the right expertise in the room for any type of project.
Okay, great. So I think maybe we've got time for one more question, and I'll do my best to, condense and aggregate. So we talked a bit about the carbonization of rock, and these, I think, maybe in the context of open pit mining, but there's also backfill and paste tailings. And is there a way to accurately measure how carbon might be captured in those forms of waste?
Well, that's the challenge, isn't it? So it depends what you mean by accurate, but I think, and that's why we focus so much on the measuring, because if it's regulation compliant, or if you want to show progress, you need to be able to measure something fairly accurately. What I would say is this is a growing area to be able to ascertain how much carbon has been sequestered and how permanently it has been stored or converted. And obviously for backfill, you can, and then there's the time dimension. So does this for now, it's being captured, and that's, Ryan, what your previous question was alluding to, how permanent is permanent. And are there, like with acid mine drainage, there are questions about, dynamic systems and how permanent they are. So that is a growing area of research, and I think mining companies can be part of that, because we all need to be able to answer that question for many reasons.
Okay, sorry, I'm going to need to step in there. Unfortunately, we've run out of time. Fascinating. To those of you who have entered questions, they will be forwarded on to the presenters, so that nothing will be lost here. Those answers will be compiled and sent to the presenters. So thank you everyone for joining. Thank you very much, Aaron and Lucinda. Michelle?
Thank you, Ryan. And thank you, Aaron and Lucinda, for joining us today. I'd like to thank all of our attendees and ask that you please fill out the short survey that pops up on your screen at the close of the webinar. A link to the video recording of this webinar will be emailed to you tomorrow. For more online presentations like this one, visit the CIM calendar of events on cim.org. We look forward to seeing you at our next Solutions Exchange webinar. Thank you. Have a good afternoon.
Bye.
Bye.